our next talk, I'm super excited to hear. Um, as you can see here, there's a large group here, all in Toronto, I suspect. These were the folks behind Guardin, I think. I don't know if I'm saying this right. But they won this 2025 Toronto um, biohackathon kind of thing. And they did this by building a toolkit for FL, but more importantly, for people working in the healthcare domain, if I understand. So I'm eager to learn all about it. We have here Chong, but also, as I mentioned before, his colleagues, Sahil, Alexander, Oscar, and Kai. Plus, I hope I got everyone's names and everything. So over to them. I'm really curious to learn more about this and see what they've been up to. So thanks for joining us.
Hi, thanks. We'll just share the screen. Can you see the slides?
Yeah, it looks perfect.
Perfect. All right. Okay.
All right, so we are Guardin. This is our team name for the hackathon project. And so I'm Chong.
I'm Alex, third year undergrad at U of T in bioinformatics and computer science.
I'm Sahil. I'm a third year undergrad at U of T in computer science and quantum physics.
I'm also a third year undergrad. I'm doing data science and computer science.
And I'm Kai. I'm a undergrad computer science student as well.
Yeah, I forgot to mention, sorry, I forgot to introduce myself. I'm also a third year computer science student studying also studying bioinformatics. And
Yeah, we are presenting today from the beautiful city of Toronto. As you can see, here's a picture of our lovely front campus. And we're actually in the basement of a library that's a bit to the right of what's shown in the picture. And yeah, I just wanted to start off our talk with talking a bit about what we actually won, Toronto Bioinformatics Hackathon. It's a student-run hackathon, which for the larger Ontario, like the province of Ontario, the larger bioinformatics community, and it is the largest bioinformatics hackathon in Canada. To build Guardin, we had a 28-hour coding window, and there were 151 participants across 25 teams. Of the 25 teams, we won the first place prize with Guardin, and we are very excited to be able to talk about it with you guys today.
all right, so I would like to introduce why we built this project in the first place. So as we can see that AI in healthcare is really skyrocketed over the past few years, and there's a lot of publications for new models for screening and diagnostic purposes in healthcare. This is really good. However, in reality, there's a lot of issues with data. So this is actually our motivation for the project. Over the summer, I was working with Dr. Chow. She is a respirologist in Toronto General Hospital, and we were trying to train a model to detect restrictive lung disease based on only spirometry data. We first tried using UHN, which is the University Health Network's own pulmonary function test dataset. However, it has a very small sample size. The data set is very biased towards restrictive cases, which resulted in a lot of generalization problem when we tried to run it in other colleagues' data from Montreal. So what we tried to do is we contacted this colleague in Montreal and we were like, can we share data so we can train a better model with more balanced data set? However, I didn't realize that in healthcare, there is an extensive process in terms of data sharing agreement. There's a ton of ethics approval, which can take months, even up to years. And to expand on the second point, there's more difficulties in sharing health data. First of all, health data is very sensitive. It has a lot of private patient information, which could cause the patients a lot of harm if the data is breached. It is also very large, namely videos, and can be really a hassle to transport between the different hospitals or data centers. And lastly, it is super difficult to anonymize. An attacker can easily identify a victim from a large database. An example of this was in the 90s, there was a genome-wide association study of many people to find genetic variations, typically like single nucleotide polymorphisms. It was open sourced, and in 2008, Homer and al. Published a paper that can find using weak correlation tests on these single nucleotide polymorphisms to identify whether a patient's DNA was in the dataset. And this resulted in the National Institute of Health having to remove all of the data set because it has been compromised, and has shown to be able to be compromised. And at the end of the summer, we all came together as a team and we decided to try to find a way to do this in a hackathon where we can solve the problem of the traditional ML being so centralized and so data-centric that all the data has to be pulled together. So we wanted to build a system that can train a model collectively using decentralized data sources, which is why.
And this is what brought us to Guardin, which is a platform for healthcare professionals to lead and contribute to federated learning projects. And so just because we said that it just wasn't feasible to move all the data in a safe and secure way to the computation, what instead we're going to do is we're just going to move the computation to the data. This is actually a quote from the Flower website. But so with the federated learning and using flower.ai. Oh, why is this went the wrong way? How do I? Sorry. There you go. And so just as a recap, right, the idea is that we're going to have one centralized server that's going to hold the actual model weights. And then all these little clients here in this picture, client 1 and 2, would both be hospitals, and these would have their own data sets. And instead of sending over the data over any kind of network where it could be compromised, we're just going to send over the weights. Is the button?
Oh, very good.
So then, yeah, so using federated learning, we're only sending the model weights over the network, which already heavily minimizes the potential exposure of information. Additionally, we're essentially training one model over all the data sets, which addresses the generalizability issue that Chong mentioned. So by combining a bunch of hospitals that could have slightly different data sets and more varied, we can end up training a global model which can generalize better. And then finally, we also implemented differential privacy on the server end. So by noising the weight slightly, this minimizes the risk of a reconstruction attack or the damage it could do. So to recap, like not only are we not sending the data over, we're only sending the weights. And then furthermore, we're noising the weight so that even if the weights get breached, we can bound the amount of information that an attacker could gain from these weights, which would make a reconstruction attack even less damaging.
Yeah, so now that our background has been well established, we're going to move on to talk about what we actually build. Guardin is an application which allows for medical professionals to easily collaborate on federated learning projects without actually having to code the models themselves or interact with them directly through code. We've developed both the Guardin desktop application, which is very easy to use, as we'll talk later during the presentation, and we are including a demo in the next few slides. We also built a Guardin server, which is an orchestrator that works with Kubernetes and flower.ai for starting and coordinating training. And as a proof of concept, we built two models, AlzheimerNet, which is a simple feed-forward neural network for predicting Alzheimer's disease given patient data, and TumorNet, a simple convolutional neural net for predicting classes of brain tumors from MRI scans. Throughout the rest of this presentation, we will be focusing on AlzheimerNet, but we built these two models just to show that the platform is really model agnostic. And no matter what model or what type of questions you want to answer in the healthcare space, the Guardin application allows you to do machine learning for it. And just to talk a little bit about our Alzheimer's dataset, it's quick from Kaggle, it's a hackathon, so we had to find something good. But it does have a lot of patient information, and it's very sensitive, obviously. You don't want to include medical history or to leak demographic details of patients. It's a simple binary classification that we made, whether or not a patient has an Alzheimer's diagnosis or not. And while the dataset is relatively small, we believe that it's a good proof of concept for expanding, and we have a very scalable architecture, as we will talk about in our demo and our tech stack.
Right. So now we're actually going to show just a quick demo of what Guardin looks like in practice. We're just going to open a video that we made. All right, so here is, here's what, where's my mouse here? Here's what Guardin looks like for a healthcare professional opening the application. Here's our demo. And so we can see, I'm just going to pause it a little bit to explain what's happening. But here this is what the dashboard looks like of the application. And so there's all these different models you could choose from, and it'll say like what kind of data set it needs. So here we're going to use the Alzheimer's predictor model, which needs a CSV. So if we click on it right here, we'll go to a new page. 1 second, here we go. And so here, as you can see, it's very easy to do. We can actually just drag and drop it. So here's Alzheimer's disease data.csv. This sort of simplification, but this is what the hospital workers would see. So you would just take the CSV, drag and drop it in here. And then when we press upload data, now don't worry, the data is not going anywhere. What this is actually doing in this step is it's pulling a copy of the model from our registry, and it's just mounting this CSV to that container so that we have the training all set up. And so it's going to load, and then there we go. And as you can see, it's going to show us the output of the Dockerized model and the data mounting. So when we did this, you'll see in 1 second, we don't show it here, but there's actually 2 laptops at the same time doing this. So this is simulating 2 hospitals have now drag and dropped the data set into this box. And then the server, we've pressed start training on the server end. And as we're going to see, it's going to start showing us the output. This output isn't very important for a special. This is more for us to be able to see what's going on. And if we scroll down, we'll see that we've digested the outputs into a much more understandable graph for the users. So this is giving us real-time updates of the accuracy and the loss throughout different training rounds. This is of the global model. And so as we can see the accuracy increasing and the loss decreasing, which is good. And here we did it for 8 training rounds. And so in a second, we'll see that it looks like it's about converged, and we can press download model weights at the bottom, because at every step, the server will send out the copy of the global model. And so when we download it, we can just download it into an NPZ file that's zipped here. And yeah. Okay, so that we just showed, this is what it would look like, one federated training of the AlzheimerNet model. So it successfully worked, and we saved it. Now I'll go back to our presentation. All right. And this also shows then that we can reconstruct the model from those weights that I downloaded at the end of the video. So this just shows us how one hospital then would take this file, the weights, reconstruct the model, and then run it on their data set, and it'll present a report of how the model does. So this is the global model applied to one of the data sets. And so what we actually did for this project was we trained the AlzheimerNet model twice. Once centralized ML, which is the traditional way, where we had there's one data set and we trained a model on it. And then once Guardin, we federated it across 2 clients. And so by studying the curves of the loss and the accuracy, we noticed that the centralized ML model converges faster. It attains roughly 82% accuracy by round 4 of training, versus the Guardin model, the federated one, takes a little longer. So we can see the slope of the accuracy curve is a little lower. However, it ends up getting to the same accuracy by maybe around round 6 or 7 instead of the 4th round, but it ends up at the same accuracy, just needs more data to converge, which we noticed was consistent with the literature, which is that the federated learning can take a little longer or needs more data to converge. However, the privacy benefit that speeds up the acquisition of data, we think outweighs the cost of needing more data.
As you saw in the demo, we have a bunch of different models that we wrote training scripts for. And the way it works when you select which model you want to federate learning for on the front end is that it actually pulls one of those different images containing our training scripts for either the AlzheimerNet or I forget the name of the TumorNet model from our Docker registry, which then runs the Flower client and our PyTorch model and communicates with our Kubernetes hosted flower.ai control plane that coordinates all of the training between all the different clients. And when you actually interact with the app, it is directly communicating with the Docker container that's running locally to get things like the training progress and all the weight updates.
So our tech stack and our backend seems pretty complicated, but the entire appeal of our app is that it's super easy for healthcare professionals to use with little CS experience. So the way we accomplish this is for data uploading, we clearly just display the types of data files that our models will accept. And then once they're uploaded, if there's like some formatting issues in the data file, then we indicate that to the healthcare professional, like exactly what's going wrong. And then here we could also implement maybe some auto formatting to make the data uploading even more seamless. And then once they press the upload data button, we send a Docker command to retrieve the model weights and then begin training seamlessly. And then we get this Docker, we get the Docker output from the server, which is pretty complicated itself. And then we parse it into something that's digestible for someone with very little CS experience. So our complicated Docker output turns into just accuracy and loss graphs, which are simple to read as if the green accuracy graph goes up and the red loss graph goes down, then that means that the model training is going well. And then our app is super portable, like our Electron desktop app. Instead of using a web app, this allows us to ensure that there's no like intermediate server where we have to upload the data. Like everything can be happening, or the entire training process can happen locally, which mitigates any privacy concerns for hospitals because all the data like stays in the institution. And then because it can be built for any OS and then downloaded on GitHub, it removes all the hurdles for institutions to upload their data.
All right, and now just to end off our presentation, we'd like to talk about a few future developments that we want to see with the Guardin app in the future. First, we'd like to improve the metrics for many things. First, those being model quality. We want to include more than just, loss and accuracy. We want to include more model metrics and make those communicable with the actual healthcare professionals who are using the app. And one big issue with actually including federated learning projects in the real healthcare space is the fact that hospitals might not have incentive to actually share their data to a larger global community. So if we include incentives for contribution, as well as weighing contributions for data quality and data variability from many different sources, this will improve both the size of the data sets that we're actually getting from many different communities, and also the quality of the data set, improving generalizability of the predictions and improving the use of Guardin as a whole. Additionally, the next set of bullet points that I'd like to talk about are general improvements to the app itself. First off, we'd like to include guidelines for both model building in case people want to add models to the Guardin architecture, or pre-processing data, where you could have guidelines for pre-processing data before it's actually uploaded into the Guardin server to actually automate that process. We also have more analytics and progress for model training, as I was mentioning a bit before when I was talking about metrics for model quality. And as Sahil was mentioning before, we have the start of a dataset auto-formatting pipeline. But if we include the actual logic to take the files and auto-format them, that would make the process a lot more easier for healthcare professionals actually using the application.
Another thing we want to add to the model is non-IID detection, which is a big issue in healthcare. If you have different hospitals that are like consistently producing different results for one reason or another, like maybe the machines are different, we want to be able to detect this, at least detect it and ideally correct it on the server end without the client having to do anything. So we can do something like, for instance, dynamically switch strategies as needed. We can, right now we're just using federated average as a strategy, but we could have a case where, for instance, the server will detect batch effects occurring, and then we'll switch to like FedNova, for instance, which is an algorithm to mitigate non-IID-ness of the data.
And finally, we'd like to focus on model interpretability, which is a very important point in healthcare settings. Because if you take a prediction from a model and you have no explanation for why it's given that, it's going to be very hard to get healthcare professionals and patients to actually want to use the information that the model is using. One thing that we found in literature are Shapley additive explanation values, which, as cited in the paper that's cited below, have actually been cited in federated learning research in healthcare settings. What SHAP values basically are quickly is they provide a little bit of an explanation for the importance of specific features and why a model would, or what features a model is looking at in making a prediction. So if this data is, processed and made more clear to healthcare professionals and patients, it could also improve the interpretability of the app. And one final point that we'd like to talk about is that the fact that Chong mentioned that he was doing work at UHN with Dr. Chow. I am also doing research at the Princess Margaret Cancer Center at UHN, which is it's a set of hospitals in Toronto that includes the Toronto General Hospital and Toronto Western Hospital and other research centers, including the Princess Margaret Cancer Research Center. And using our connections at UHN, I am under Dr. Benjamin Hyde-Keynes. We are hoping to actually explore use of federated learning in these healthcare spaces.
See the citations, and thank you, and check out Guardin on GitHub.
Yeah, so that's the end of our presentation. Thank you so much for listening.
Amazing stuff, guys. Very cool. So yeah, if anyone wants to ask a quick question right now online, feel free to raise your hand if you're in the webinar. I'll keep my eye out. Oh, we do have I see. We have a question, anonymous question. Question is, hey team, absolutely love this project and your roadmap. How long did it take you to build the app?
It was a hackathon project. We had 28 hours to code. It took us about 14-ish, but we were doing model training too, and it took a while. Debugging took a bit too, but yeah, everything was able to fit within that 28-hour window.
We didn't get a lot of sleep though.
Yes, that is very true.
Yeah, I can imagine. Were you first time Flower users on that event?
Yeah.
Really? Wow, that's awesome. Far out.
Oscar did a lot of reading before the
Yeah,
hackathon.
we did literature review to actually make sure that we had the points for next steps, what research has actually been done on federated learning in the healthcare space, that sort of thing.
Yeah.
Awesome. Let me take a look on Slack. A question is basically saying how can you change the model architecture, I guess, or even just model type? Yeah, I guess from the view that you showed, it wasn't so obvious about how you might change it.
Yeah, basically, the way we did it, we basically just wrote a couple of models, and the idea is like since we have them on this registry, you can just click on whichever one you want. So,
Go back to
it's back to the demo, but basically there's a lot of different buttons you can click, and then clicking on any one of them here, if you click on this, it'll bring you to that next page for that model. So you can't see the mouse in this video, unfortunately, but then we clicked on Alzheimer's predictor, we clicked select Alzheimer's predictor, and then it brought it to that second page.
I see. So you pick discrete models where everything or everything is already predefined.
Yeah, so we're hoping at some point people will contribute their own models to Guardin, and then they'll show up on that page.
Oh, very interesting. That's cool. Yeah. Let me see. Oh, another question in the window. Yeah. There's so many windows. Oh no, we answered this already. Okay, fine. Good. Okay, well, I mean, that's cool. Amazing project, guys. Really impressive. I think everyone should check out Guardin. It's amazing stuff. Great.
Thank you so much for the opportunity.
Yeah, thank you. Great.